We are here to study fluids. We're going to begin with static fluids, and I'm going to break it up into a couple of parts so that it is not too long. Okay, so first off, what the heck is a fluid? A fluid is anything that flows, so that would be a gas or a liquid. They do not have a definite shape, so they are a little bit different than everything we learned about in AP Physics 1 that concerned solids. They exert a pressure on the container that confines them. Now, gases and liquids are vastly different. Gases are far apart and they're not connected. The molecules fly around free. They can expand and to fill any container, and their volume can be changed. So these are unique properties of gases, which we'll talk about later when we get into thermodynamics. Liquids are very different. They're heavier, they're bonded together, so they stick together, and they have a definite volume, and they have a surface, a top surface, when they're in like a glass or something, or in a lake. So they're different than gases. So we're talking today just about the unified properties of both gases and liquids, the properties of fluids. Background information, things that you need to make sure that you know. Remember that volume is in units of meters cubed, and we can find volume for a sphere or for a cylinder. All those equations are on our equation sheet. Don't freak out. Remember density from chemistry class. That density, this is our symbol for density, the Greek letter rho, is equal to mass divided by volume. And that also means that you can find the mass if you know the density and volume of the object. So like for a liquid, a lot of times we'll know the density of the fluid and we'll know the volume that it takes up. So we can multiply those together to get the mass. Remember pressure, our units are pascals, which is newtons per meter squared, which is a tiny unit, so we'll end up with a large number for pascals a lot of times. Pressure is the perpendicular force divided by the area. We'll talk about this perpendicular a little later. And the force is equal to pressure times area. So if you take the force and multiply by the area both sides, this is important because we need this when we're doing free body diagrams, pressure times area. In the table at the right, you don't have to have any of these memorized, except you might want to know that one right there for water. Other things to note is that density of liquids, all the ones in blue here, are quite large compared to the density of gases. Density of gases is really small. It's not zero. Fluid behavior has two parts, both static and dynamic. We're going to concentrate on the static today. So what causes pressure in a fluid? Okay, so everything's made up of molecules or atoms. These tiny atoms and molecules are moving around at high speed, and they're confined, in my picture, in a container, a rectangular container. Every time it hits the surface, it changes momentum. The momentum changes, and there's a tiny collision with every atom. And that produces a tiny impulse, or an impulse is necessary to change the momentum of the gas particle or liquid. It doesn't matter. Now I want you to notice that say like, look at this one right here. This one comes down, hits, and bounces off. Its horizontal momentum is not changing, only its vertical momentum. So that means it's a vertical impulse on this wall. And that means that there is always a perpendicular change to the momentum, which causes a perpendicular impulse, which means the pressure that's produced, which is the force over the area, is always perpendicular to the surface. Okay? That's really important. So occasionally on the test, I'll ask you, what's the mechanism that causes this pressure or this force in a gas or a fluid? And it's these collisions of individual atoms that are changing momentum, which produces an impulse, and the sum total of that is all of that force, divide the area, and you got pressure. So here I've got a piston here. It's got a movable top, and it's initially wide open like this, all full of gas. That's the initial state. Over here I put a mass on the top of the piston. It's pushed the piston down, and there's the final state in equilibrium. initially the piston's in equilibrium right here, and then after I put that mass on it, it's compressed and it comes to a smaller volume and it's in a new equilibrium position. What's the physical mechanism that creates the pressure inside the cylinder? Well, we just talked about that. It's the collision of, in this case, gas molecules colliding with the container. Which state has the higher pressure, the initial state or the final state? Well, I think we would all guess that it's the final state would have more pressure inside. Okay, well, what are the physical changes to the gas that allow it to hold up more weight? Okay, why is this able to hold up this weight? All right, so here's the deal. I want you to notice all these molecules here are all spread out, and here they're compacted in much tighter. So what happens is that when they're compacted in tighter, then there's going to be more collisions per unit time against this piston and the sides of the cylinder. So therefore, there will be more tiny impulses, therefore more pressure. So this is why when the volume decreases or gets compressed, the pressure goes up inside the gas, because there's more atoms smashing up against the piston. Number 4 over here asks, what is the initial pressure in the cylinder? Okay, there's gas inside the cylinder pushing up on the piston, and if the piston is free to move, then it would pop out unless there's something up top pushing down. Now there's no weight up here, so what's pushing down must be the atmosphere from the outside. So this must be in equilibrium if it's not moving, so therefore the pressure on the outside must equal the pressure inside the cylinder, inside the gas. All right, our final question is, what is the final pressure of the final state? Okay, in order to solve this, we need to set up a free body diagram. So this is the piston. There's a gravity force pulling the weight or the mass down. There's the force from the outside atmosphere pushing down on the piston. And then there's the force from the gas on the inside pushing up. So this object is in equilibrium. The acceleration is 0. So the forces have to cancel out. Therefore, these two forces down equal the force from the gas up. The force from the atmosphere and the force from the gas can be calculated by taking the pressure and multiplying by the area. Now, I haven't told you why this is yet, but the pressure in the atmosphere is 100,000 pascals, and we can pick that up from our equation sheet. It's on the constant side of our equation sheet. So atmospheric pressure times the piston area gives us the force from the atmosphere. The mass times gravity gives us the gravity force down. And then the pressure in the gas times the area of the piston is this over here. And solving, we get 100,196 pascals. Now we know it's these collisions now that cause the pressure. But there are some contributing factors to this pressure. The first is the thermal effect. As the temperature goes up, the velocity of the atoms gets faster. That makes the kinetic energy and the momentum of the atoms get greater. This causes the pressure to go up. So in general, as the temperature goes up, the pressure in a fluid goes up. This is particularly true of a gas where the molecules can move free. Now, the gravitational effect. The atoms at the bottom of a fluid, so take a look at this glass of water. The atoms down here at point B have all the atoms above, including the atoms at point A, to push up to keep them from falling. Gravity is pulling all of these at A down towards B. But if the fluid is static and not moving, then that means that these have to push more than the ones at A have to push up, because they don't have to hold up as much. So this means that the deeper you get in the fluid, the greater the pressure. And you should know this because you've all gone swimming and swam to the bottom of a pool, and you can feel that extra pressure. Or you've been in an elevator or a plane. As you go up, your ears will pop because the pressure decreases. Static fluid pressure. For liquids, the fluid pressure increases with depth due to this gravitational effect. And here is our equation for that. The pressure inside of a fluid at any point is equal to the pressure that's on top of the fluid already, plus the density of the fluid times the acceleration caused by gravity times the depth that you are in the fluid. So this is the extra added pressure in the fluid because of the gravity effect pulling all that fluid above down. So all we care about is that fluid up above. Gases have a really low density, and thus the pressure changes very little with height. The gravity effect has very little difference on gases. So unless we have a very, very large height difference, we're going to assume that the gases have a constant pressure. And so this is where we call this average atmospheric pressure. It's actually 101,325 pascals. But on the AP test, they round it to 100,000, which is nice of them. So if we had a glass of water like this, and the water level was here, and we punched a hole in the side here, the water would squirt out. And this is our difference in height. So if we had another glass over here and the water was up high like this and we punched a hole in right here, the water would squirt identically the same if this delta height was the same. So all that matters is the difference between the top and where you're at, that height difference. We have a tiny container like this where we punch a hole in the side, the water is going to squirt out. And if we have a really wide container and we punch a hole in the side, that as long as this height difference is identical, then the water is going to squirt out the same because the pressure here and here will be exactly the same. Okay, so which water tower will produce the most pressure at the bottom? We know that answer, that the width or amount of water makes no difference, only the height. At the bottom of each of these water towers, the pressure is identically the same. Only the height matters. Okay, which location has the greatest pressure? P1 or P2? Well, remember the pressure here is the pressure on the top, P naught, plus the rho GH difference between here and here. And that difference is the same as here and here. The height difference is identical. So that means along any horizontal line inside of a static fluid, the pressure is going to be identical. The pressure at P1 and P2 has to be the same. Here is my situation that I have. I've got water here and I've got water here. So at this point here, we're going to have a certain pressure. The pressure from the atmosphere on top, plus this delta height pressure right here. So the pressure right here equals P plus P naught plus rho G delta H. And this point right here will have a similar thing, except we have a larger delta H. So the pressure here will be P naught, which is the same, because it's open to the atmosphere on both sides, plus rho G, but this is a greater delta H. So that means the pressure here on the left will be greater than the pressure here on the right. And that means that the fluid will flow in this direction because there's a greater pressure here than here. And that'll occur until this side over here gets to the same height as this over here. This is why on Earth we have sea level, because everything is the same height and before it becomes static. Okay, calculate the pressure right here. Well, we know a few things. We know that the pressure here has to be the same as the pressure over here if it's a static fluid. So all we have to do is find the pressure at this point, and it'll be the same as at that point. So the difference in height between here and here is 0.9 of a meter. This is 1 meter, so that's 0.9. So I get 0.9. The pressure at 0.9 of a meter equals the atmospheric pressure on top plus rho G delta H, which is the density of water, times G times 0.9, and I get 101,820. All right, if this was angled at some other direction or if it had some other weird shape, it wouldn't make any difference. All that matters is this height difference. All right, we got ourselves a scuba diver here. How far below the surface of the water does the scuba diver have to go in order for us to double the pressure on the scuba diver?
Now, right up top, this is, I assume there's an atmosphere up here, so the pressure up top would be 1 atm, or 100,000 pascals. So that's what you would have if you were up here. But the scuba diver goes down here, so the pressure down here would be 2 atm, or 200,000 pascals. So in order to get that pressure, we need P naught plus rho G delta H. There's our delta H. And so this is 2 atmospheres, 200,000 pascals. And this is 1 atmosphere, 100,000 pascals. Plus rho, density of water, 1,000 kilogram per meter cubed. Running out of room. And this is G. I'm just going to use 10 to make the math simpler. Meters per second squared times, and I'm out of room, delta H. So if I subtract and divide, I get a delta H of approximately 10 meters deep. It's about 30 feet. So if you dive down 30 feet in water, you'll have 2 atmospheres of pressure on your body. Okay, let's talk a little bit about barometers. Now, barometers are a weird device that's tube gets filled up with something like mercury, and then it's dumped over into a container like this, and the mercury starts to flow out. But as this puddles down here, as long as you keep this edge below the surface, it will go down so far, and then it'll stop. So, a couple questions for you. First of all, what's up here? And the answer is nothing, because all that mercury is flowed out. Flown, poured out. So that's a vacuum up here. The pressure in a vacuum is 0, okay? So let's figure out what this height will be here, all right? The pressure up top is 0, because it's a vacuum. And we're looking for this height. First thing to realize is we have out here 1 atm, or atmosphere, or 100,000 pascals. And that these two have to be the same pressure because they're at the same height. So the pressure at B must equal the pressure at A, which must equal 100,000 pascals. So the pressure at B also has to equal the pressure on top plus rho G delta H. Well, the pressure on top is 0 because it's a vacuum. So you get 100,000 pascals must equal the density of mercury in this case. So you can go back in the video and watch, or look it up online. Kilogram per meter cube. It's 13,600 kilogram per meter cube. The acceleration caused by gravity is around 10 meters per second squared. Delta H. So delta H is going to be approximately 0.74 meters. And it'll stop. And as the pressure outside fluctuates, this will move up and down. As the pressure goes up, this will push up higher. As the pressure outside, like a bad weather day like it is out today, then the pressure is less, and this will flow down a little bit. Which brings us to, how does a straw work? All right, it's actually kind of complicated. Outside here, we have an atmosphere all around. And that's pushing down on the top. So the pressure in the fluid right at B must equal 1 atmosphere. The pressure at point C must be greater than the pressure at B, which equals 1 atmosphere, because it's deeper in the fluid. Now, if we look at the cup from the side, and the straw is just sitting in here, then the pressure here and the pressure here must be the same. And the pressure here and the pressure here must be the same at 1 atmosphere. So this is point B, and this is point C. Now, in order to get the fluid to come up the straw, you need to lower the pressure here at point A. So you put your lips on it and you inhale. You lower your diaphragm, which lowers the pressure inside your lungs, which lowers the pressure here. Now that does not pull the liquid up. What happens is now the pressure up here is less, like in the barometer, and so the pressure is greater here, and it pushes the fluid up the straw. If you would seal the top of this so that the atmosphere could not get into this, then you wouldn't be able to suck any liquid up the straw, okay? Because you couldn't, the pressure inside wouldn't increase. It would decrease as the water level goes down. What's the pressure in the chamber here? This is called a manometer. It's just a way that you can have a gas inside here, and it pushes out through this tube, and it pushes this liquid up. And knowing the difference between this point A and the top, in this case it's 20 centimeters, you can work backwards to figure out what the pressure is here at B, and that has to be the same pressure as A, which has to be the same as the pressure of the gas inside the chamber. So it works like this. So the pressure inside the gas must equal the pressure inside the fluid here at point A. And since the fluid is static, that has to be the same as the pressure at point B, which has to equal P naught, the pressure on top, which we assume is atmospheric, plus rho GH for the fluid right here. And if it's water, if this fluid is water, then the pressure inside the gas would be 101,960 pascals. Okay, what if there was fluid on this other side? Let me show you what that means. What we mean is every once in a while I'll ask a problem like this, where there's a fluid here, and there's a fluid over here, and there's like a interface between the two. So this is fluid A and fluid B. So fluid B is heavier, denser, because it's pushing fluid A up. And you can relate these two fluids because along this line right here, the pressure here in fluid B has to be the same as the pressure here in fluid A. So for fluid B, you would have the pressure here would equal the atmosphere on top, plus rho for fluid B, G, and this would be H1. And then over here, this pressure has to equal the pressure on top, which we assume is atmospheric again, plus the density of fluid A times G times this height, which would be H2. And these two would have to be equal. So you can see that the P naught drops out, so the density of B, G, H1 has to equal the density of A, G, H2, and that cancels. And so you can figure out whatever the question asks. Okay, so you have internal blood pressure. Your heart is pumping blood to all parts of your body. The pressure inside your body is greater in your veins than atmospheric. Otherwise, your veins would collapse from the atmosphere. So that internal blood pressure That's why if you get cut, that's why you bleed, and it pushes outward into the atmosphere. So in order to get, say you're a victim in an accident, then in order to get blood into your system, you have an IV bag, and all they have to do is hold that up high, enough height, so that this difference in height adds a rho g delta h height difference that increases this pressure greater than your blood pressure, and it will push the fluid into your body then. Alright? And in an emergency, say like someone that's been in a bad accident, what they can do is they can take this IV bag and they can just push on it, press it with their hands. And when they do that, it will push the blood into your body. Pretty cool.
All right, I think this is our last thing, Pascal's principle. The pressure exerted at one point in a confined fluid is distributed, D, throughout the fluid undiminished. So you know this from a toothpaste tube. When you squeeze it, it comes out no matter where you squeeze it. The pressure is sent everywhere through the fluid, undiminished. This device right here is called a hydraulic pump. So when you push down on this one, that extra pressure you make here is transmitted to this side, which increases the pressure on this side and can make this piston go up. The cool thing about it is if you have a small area and you push down here, then what you end up with is a small area in the denominator. So for a reasonable size force divided by a small area, that gives you a big pressure, and that big pressure is transmitted over here. And then if you have a large area over here, then that means this force too is going to have to be much larger in the ratio of the two areas. So if this area is 100 times bigger than this area, then you get out 100 times more force. Now this seems like a magical increase in force that's going to violate conservation of energy. But it doesn't, because what happens is this volume of fluid that flows over here doesn't fill this up very fast. And so what we end up with is a small increase in height. So the work that you get output over here is never any bigger than the work that you put in over here. So it doesn't violate conservation of energy. So that's our first part of static fluids. We're going to cover buoyancy force in our next video. See you in a bit. Bye.